So a transistor is the building block of an amplifier. A transistor, let's say if it's a BJT, the collector current is a factor of the base current. And usually this factor is in the order of 100. That means if you have a certain base current, the collector current is going to be 100 times the base current. So there's naturally a current gain there. So essentially you're going to tap that feature of the transistor, but build something over it. The transistor becomes the building block, but outside the transistor building block, you have this DC supply. It is this DC power that is connected to make the enough R out, the RF power to come out. Because this guy, the RF in, the power is very low. It is not that the amplifier magically gives a high power. Yeah, energy has to be conserved. Somebody has to give that energy. It is this DC power supply, the PDC, plus the P in that gets converted to the RF out. And in that process, you want to bias this transistor, which we will see what that means. And you will have to have input and output matching network. So this whole package is what you call it as a amplifier. So for example, if you take a look at a common emitter amplifier, for example, you see that always the collector current is going to be a factor of the base current. And beta is typically in the order of, let's say, 100. Yeah, that means the base collector current is 100 times the base current. So by controlling the base current, you know whether the transistor is on or off. If the base current is high, then the collector current is high. That means the transistor is on. If the base current is low, then the collector current is 0. That means the transistor is off. Yeah. But specifically, if you notice, there are what are called as these resistors that are called as biasing resistors that will determine the Q point or the operating point of this transistor. What do we mean by that? If you look at, let's say, the collector emitter voltage, the VCE that we are looking at versus the AC, the collector current that flows through the transistor, you would obtain a set of curves like this, which change for different base currents. It changes for different base currents. Now, if my input signal is changing, essentially my VBE is changing, the base emitter voltage is changing, which in a way corresponds to the change in the base current. Whenever my RF input is 0, all that I have is a DC bias condition where this is really a resistive divider network. If I have a 20 kilo ohm resistor followed by a 3.6 kilo ohm resistor, and if I supply a VDC here, this is R1 and this is R2, I can determine what is the voltage at this point. That is going to be simply R2 over R1 plus R2 times VDC. It's a simple resistive divider. So you determine what should be the DC operating point. And that at that operating point, the collector base current is going to be 46 microamperes. So that 46 microamperes curve is somewhere here, where it is below the IB curve of 50 micro. Yeah, it is somewhere here. That's the Q point or the operating point, the quiescent point of this transistor amplifier. Now, when you have a certain load of, let's say, 1.2 kilo ohms here, which is what this resistor is, if you monitor the voltage swing across this resistor alone, so that is determined by the IC that flows, isn't it? The collector current that flows through there. So for a small swing in IB, which is typically in the order of 50 microamperes to 100 microamperes, for this small swing from 50 to 100 microamperes, you see that the IC swings from 7.7 milliamperes to 2.2 milliamperes. So you got a gain there, right? When I inject a voltage signal like this, my base current is going to change in microamperes, swinging in microamperes. I got 1,000 times factor in terms of milliamperes here. And that milliampere current, when it goes through the load line, where this is the load is 1.2 kilo ohms, you're going to get a sufficient voltage output that is going to swing much higher in power. So that's essentially the working of a transistor as an amplifier.